doing a brief summary of vectors in R2. R2 being the plane, the XY plane if you wish, but any 2 by 2 plane. So this board represents a 2 by 2 plane. This arrow represents a vector that we call V. This arrow represents a vector we call W. This one represents a vector we call U. Each vector has a length that will stay the same no matter what we do with the vector, and a direction that also stays the same no matter what we do with the vector. Okay, well, we can do anything with the vector as long as we don't take it out of the plane, because we're kind of confined to the plane, and as long as we don't change its length or direction, meaning we can move it around. So we can move these vectors around to get the sum of two vectors. Okay, there are two ways to do that. Okay, here's the V vector, here's the W vector. They're both drawn with a common initial point. I can get the V plus W vector by just drawing a W vector up here and a V vector here, which creates a parallelogram. And the V plus W vector is the diagonal of that parallelogram. Another way to look at it, if I was to draw the V vector from some initial point, and then from the head of the V vector draw the W vector, that's called head to tail, V then W, then the vector from my initial point to the terminal point of V to the terminal point of W will be my V plus W vector. And of course, if I did W from the initial point and then V from the terminal point of W, I would complete a parallelogram and end up in the same point, so that my W plus V vector would go from the initial point of W to the terminal point of V, and would be exactly the same as the V plus W vector. So V plus W equals W plus V. These vectors are, when addition of these arrows is commutative. And we see the same thing with the U and V vectors here. Either head to tail with our U plus V vector from the initial point to the terminal point, or V plus U the same way, or just draw the parallelogram and the diagonal is the sum of the two vectors. We always go from the initial point of the first vector, though, to the terminal point of the last. So by the geometry, parallelogram, and so forth, we have a parallelogram. U plus V equals V plus U, because of the properties of parallelograms. Now, we can do a multiple of a number in a vector. Okay, here's W. What would we mean by 2W? Well, 2W probably means W plus W. So we do W plus W. Now to do W plus W, we don't get a parallelogram because W is in the same direction as W, but we can do the start here and draw W, and then head to tail draw another W. Okay? And now we see that W plus W is a vector that's twice as long as W, but in the same direction. Then we call that vector 2W. So 2W is just W plus W. Right here is our 2W vector in blue. Okay? Now what about minus W? Okay, well, let's see. If we did 2W minus W, or 2W plus negative W if you wish, we should get back to W. So here's 2W. What do we have to do to get back to just 1W? Well, here's 1W. We have to go back a distance equal to the length of W in the direction opposite W. So we have 2W and minus W equals W. So minus W has to be a vector in the of the same length as W, but in the opposite direction. Okay, what about negative 3W? Well, that would be 3 negative W's, 3 vectors equal in magnitude but opposite in direction to W. So here we would have our negative 3W. Now, question. And this is leading to something pretty important. We have to kind of digress to answer this question. But the question is, are there multiples of W and U that add up to 3V? Well, what's that mean? Well, 3V means 3 V's. So here's a v, here's a v, here's a v, here's 3v. It's a vector that has the same direction as v, but 3 times the length or magnitude. Okay? Now how do we get a multiple of u and a multiple of v to add up to 3v? Well, here's 3v. And here's a white line in the direction of the vector u. So we put the vector u at the same initial point as the vector v, and we draw a line in the direction of u. Now if we move along that line, in what direction do we have to move to get to the tip of the 3v vector? Well, we have to move in this direction, we come up a little higher. We have to move in this direction, we come up a little higher. We have to move in this direction. And if we come up too high, we have to move in this direction. Now, each of these directions was kind of above the vector w, and I'm just using that in a very vernacular sense. This vector would go down below w. If we go to just the right point on this line, we have a vector in the direction of w. How do we find a point on that line? Well, we just draw the vector w right here, then we draw the line through the vector w and through the point at the tip of the 3v vector until we hit the line that we drew parallel to u. Then, if we draw a vector from here to here, that's a multiple of u. And a vector from here to here is in the same direction as v, so it's a multiple of v. So we have a multiple of u plus a multiple of v equal to 3v. Now we can estimate that multiple. I estimated that this vector is about 3.2 times as long as the u vector. I estimated that this vector is about 2.7 times as long as the w vector. Now I'm estimating from a bad angle here. I don't want to get down here and block the screen while I'm making my estimate. So, it's not going to be a great estimate, but I estimated that v would be 3.2u plus 2.7w. Now there's a way, and in a minute we'll see how we can put numbers on vectors and actually use a little bit of mathematics to determine what multiple of u and what multiple of w add up to v, assuming it's even possible to do that. If w and u were in the same direction, and that was not the direction of v, there'd be no way to do it. Okay, so u and w have to have different directions in order to add up to 3v, which doesn't have the direction of either.